Let's dive right into this explainer. If you've ever poked around the greatest unsolved mysteries in mathematics, you have absolutely heard of the Riemann hypothesis. I mean, it's effectively math's holy grail, right? An intricate puzzle about prime numbers that has stumped the absolute brightest minds for over a century. Well, today, we're exploring a fascinating new monograph by mathematician Fred Yeh. And listen, it's not just a short paper. It is a massive, skyscraper-like architectural blueprint designed to finally solve the Riemann hypothesis and its broader cousin, the grand Riemann hypothesis. Yeh is proposing a unified spectral-geometric proof framework, and we are going to walk through exactly how it's built from the ground up.
But here is the core problem that has plagued mathematicians for decades. How do you prove the unprovable without, accidentally cheating? Yee points out a massive trap that previous researchers fell right into. When trying to prove the Riemann hypothesis using geometry, it is incredibly easy to accidentally assume the positivity of a certain mathematical space right at the very beginning. But that positivity? It's mathematically equivalent to the Riemann hypothesis itself. If you assume it to prove it, you're just trapped in circular logic. Yee's entire blueprint is specifically designed around avoiding this exact trap.
So, here is our path through the math today. 1. The ultimate math puzzle. 2. Avoiding the circular trap. 3. Prime orbits and spectral flow. 4. The p-adic upgrade. 5. Scaling to infinity. And finally, 6. A verifiable blueprint. Let's get right into it.
Section 1. The ultimate math puzzle, the Riemann hypothesis and Weil positivity.
Okay, to really understand the trap we're talking about, we first have to wrap our heads around Weil positivity. There's something called the Weil explicit formula, which essentially transforms the zeros of the zeta function into a distributional identity involving primes. But here's the catch, and it's a big one. Declaring the completed Weil quadratic form to be positive is mathematically equivalent to the Riemann hypothesis. Declaring this space positive without rigorously proving it first is the exact circular trap we just talked about. You literally cannot simply build a geometric space, say, hey, this space has positive norms, and then claim you've solved the Riemann hypothesis, because proving that positivity is the entire game.
Moving on to Section 2, Avoiding the Circular Trap, de Brange's versus Sobolev-Suzuki.
Think of this as the old way versus Yee's new way. On one hand, we have the de Brange's trap. Now, de Brange spaces are incredibly powerful for studying entire functions, for sure. But using a positive de Brange's Hilbert realization to prove the Riemann hypothesis? That's circular logic. Why? Because that space's positivity inherently assumes the hypothesis is already true. On the other hand, we have Yee's Sobolev-Suzuki route. This route is actually safe. It builds the proof domain in a standard Hilbert space that exists entirely independently of the Riemann hypothesis. By using this non-circular framework, Yee ensures that absolutely every single step is built on solid, independent ground.
Section 3. Prime orbits in spectral flow, mathematical clocks.
We start with something called the Kanis-Kansani scaling site. Now, in this framework, every single prime number, 2, 3, 5, 7, acts just like a closed periodic orbit. Think of it exactly like a mechanical clock, where the circumference, or the length of the orbit, is exactly the natural logarithm of that prime number, log p. This gives us a really concrete, physical, geometric object to work with for every single prime in existence.
So what does spectral flow actually look like in practice? Imagine we're tracking a mathematical value, an eigenvalue, as a parameter changes from 0 to 1. You get this single diagonal line crossing the horizontal 0 line perfectly in the middle. It's exactly like a clock's hands crossing midnight. Spectral flow counts these signed crossings. For a basic one-dimensional prime orbit, the spectral flow is exactly 1. It crosses 0 exactly once, heading right in the positive direction.
But what happens if we scale this up? What if we multiply that simple prime circle by an even-dimensional geometric shape like, say, a torus? Well, by adding a transverse dimension, it acts as a multiplier. For a transverse index of q equals 3, instead of one lonely line crossing 0, we suddenly have 3 distinct branches crossing 0. The prime orbit provides the direction of the crossing, but this new transverse geometry provides the multiplicity.
Section 4. The p-adic upgrade, Fargus-Fontaine slope clocks.
Now, a simple real circle of length log p, that's really just an analytic proxy. It's a stand-in. To get some real mathematical horsepower, Ying upgrades this basic prime orbit to a Fargus-Fontaine slope clock. I know it's a bit of a mouthful, but this utilizes local p-adic geometry, which actually contains a much richer structure. We're talking things like residue degrees, slopes, and finite torsion defects. The classical prime orbit gets replaced by a Frobenius normalized slope circle, which ultimately gives the entire mathematical framework an incredibly powerful modern engine.
And here is the major payoff of that p-adic upgrade. Remember how we needed a completely separate transverse shape to get multiple crossings just a minute ago? Well, now the Farg-Fontaine geometry supplies it naturally. The finite modification defect perfectly supplies the finite multiplicity of the spectral crossing. Basically, the defect space dictates exactly how many times the eigenvalue branch crosses zero. It's a rigorous operator-theoretic calculation that is entirely local and perfectly controlled.
Just to keep our bearings here, let's break down the author's 3 vital layers of methodology. First up is spectral flow, which gives us integer-valued local crossing data. Second is the trace layer. By applying a mathematical translation group and damping factors, Yi extracts the exact prime power weights needed for the explicit formula. And finally, the determinant layer. Finite self-adjoint determinants only have real zeros. So if you can prove these determinants converge correctly, Hurwitz's theorem basically guarantees that your final global function will only have real zeros.
Section 5. Scaling to infinity. The Sobolev-Suzuki framework.
But of course, we hit a mathematical roadblock here, called the Fredholm obstruction. If you take all these beautiful, perfect local prime clocks and just naively add an infinite number of them together, you hit a brick wall. As the primes get larger, these spectral gaps shrink towards zero. Zero then becomes an accumulation point, it enters the essential spectrum, and suddenly your operator ceases to be Fredholm. In plain English, the math just breaks. You absolutely cannot just sum up the primes and call it a day. So how do we fix that broken math? Well, Yi deploys the Sobolev-Suzuki framework. Instead of a naive sum, we use strict analytical controls, specifically things like weighted eigenvector convergence and trace class resolvent convergence. These act as the analytical engine to safely scale those finite local determinant approximates all the way up to the infinite global completed zeta function. And the best part, it does all of this without ever assuming Weil positivity.
Which brings us to our final part, Section 6, a verifiable proof blueprint, the ledger.
This right here is the verification ledger. What Ye does is separate what is unconditionally proven in the finite realm from the infinite limiting assertions. For the infinite passage, Ye lays out this incredibly concrete step-by-step checklist of 7 specific estimates, from variational uniqueness down to regular normalization. Listen, this isn't just academic hand-waving, it is a highly specific list of analytical tasks left for the mathematical community to actually verify in standard Hilbert and Sobolev spaces.
I absolutely love this quote from the source text because it really shows the rigorous standard the author is holding to. It reads, "The monograph, therefore, gives a complete and falsifiable spectral geometric closure architecture." Ye isn't out here claiming the Riemann hypothesis was magically solved yesterday. No, Ye is providing a completely falsifiable blueprint. If those 7 estimates are verified, the math converges, the zeros are proven real, and the Riemann hypothesis is officially solved.
As we wrap up this explainer, I want to leave you with this provocative thought. The blueprint is built, the foundation is completely non-circular, and the p-adic geometry is totally sound. But will the ledger actually hold up? Will the mathematical community be able to verify these 7 highly specific estimates and finally close the book on the ultimate math puzzle? Thanks so much for digging into this incredible architectural blueprint with me today.